Hello, welcome to session number 32 in the series Analog Circuit Design using ADS. My name is Anurag Nigam, and though this is not ADS, but this is in the same series as Analog Circuit Design. Now, as promised in the last session, I am going to present here a 40 gigahertz PLL in a 130 nanometer CMOS technology. Right, so this process is Silterra, it's a Malaysian fab. Okay, so here, what I'm showing here is the fractional N PLL, which operates from 37 to 40 gigahertz. This is targeted for 5G applications. And as I did in the previous session, I'm going to detail some of the blocks here. Compared to the previous design, which was for 6G application, it was from 98 gigahertz to 108 gigahertz PLL in a 7 nanometer FinFET process. Compared to that, this one is in 130 nanometer process, and this is 37 to 40 gigahertz for 5G applications. The challenge here is frequency division, right? So what this one has is a VCO over here. So this VCO, if I go inside this, okay, so this VCO basically sits over here. So this region is a VCO. The left region is a VCO. So here you have these cross-coupled NMOS, and then there are two inductors, and these are the two transistors which are used as variable capacitors, right? And these are controlled by the control voltage here, and these are biased using a wide swing cascode over here, right? So this is a wide swing cascode. Now what sits below here is basically the output is buffered, so that when this VCO drives uh, the mixer, right, for up conversion, right, or down conversion, that mixer basically loading is taken care of by this the small amplifier. So the output over here across these two differential output is a very large swing, because the supply here has two inductors, so it is going to go beyond VDD. So basically VDD is 1.8 volts, and it is going to go up to 2.8 volts. So from 1 volt to 2.8 volt kind of swing is there here. Now that basically is curtailed to VDD here by this amplifier, right? So the output of that feeds into the first stage, which is again the similar topology, but then these MOS devices, they are basically injecting the output from the VCO into this, and this is an injection lock divider. So this divides by 2, right? Following that, there is another injection lock divider, which again divides by further by 2, and then the third one further divides by 2. So there are 3 injection lock dividers, which in total divide by 8. So let me just make sure I'm recording. Okay, so in total they divide by 8, and then the output is level shifted and then given to a differential NOT gate, or a PPCL NOT gate, which is a very simple NOT gate. Let me just go into this. Okay, so this is a PPCL NOT gate, right? Okay, so this is the VCO topology here, and the phase noise of this VCO is the similar to that of the other VCO which I demonstrated earlier in the previous session. Now coming back here, the output of VCO is available over here, right? And then the divide by 8 is available over here. So this divide by 8 is driving this multimodulus divider, which is 8-bit wide, like similar to the previous design in the previous session. This is also 8-bit wide multimodulus divider, and so there are 8 2x3 cells, and each one basically looks like this, right? So this is a transmission cell based divider. So let's do a little bit of maths here. So basically this frequency is, let's say, 37 to 40 gigahertz. So let's bring in a calculator here. So 38 and a half is the mid value. So 38,500 megahertz is the output frequency. So it's initially divided by injection log divider by 8, right? So we are left with 4 gigahertz, right? We are left with 4,812 megahertz, 0.5 megahertz, right? Now this one is further uh, divided with by this MMFD. So the crystal here is 10 megahertz. Okay, what happened here? Cancel. So it's 4,812.5 divided by 10. Divided by 10. So the count is 481.25. So this 8-bit divider goes from a divide ratio of 256 to 511. So this basically fits into that. So from there, I'm going to minus 256 from there. So that's the base count. So the fractional count is 25.25. And then this is the base count, or the course count is 225. Then from sigma delta, so there is a mesh 111 over here. Let me just go here. So there is a mesh 111 over here, which has the similar topology as the previous one. It's just that this is implemented in 130 nanometers. So there's not much of a difference here. Now this is an adder to add the output of sigma delta to the course count, right? So to the course count. So what will be the course count? It will be -3 from here. So if I go to calculator, okay, so if I do a -3, so my count will be 222, and 0.25 is the fraction. So let's do this programming calculator. Decimal 222, that is equivalent to 1101,110. So this is 1101,110, right? So this is the course count. The fine feed will come from here, so that is 0.25. So let's do that maths also. So 0.25, that's going to be multiplied by 65536. So that is 16,384. So let's see in binary. So if I go to programming, 16,384. 16,384, right? Okay, so that count is 0, 1, and then all zeros. So that is fed into the sigma delta modulator. So this is basically 0, this is 1, and then rest are all zeros. So this is fed to that. The output of the divider goes to the PFD. PFD is also the same topology. So if I go in here, PFD is the same topology, right? It's just that I'm not using CC bar here, though it is the output here, but it is not connected anywhere. Okay, so I'll show you that later on. So what's unique about this is the charge pump. So the two things which are unique about this PLL is first is the injection lock dividers, which I'm going to demonstrate, and the second thing is the charge pump. Now, if I go in here, this is similar to the previous charge pump on the right hand side. CC bar are not being used, so they are just terminated into caps. So I didn't bother to throw them out. Okay, so what you see over here is this is a PMOS wide swing cascode PMOS current source, which is high output impedance, which we have seen earlier also. This is a NMOS wide swing cascode current mirror with high output impedance, and so there are two sources of current here. So these two are the sink currents. So if you follow them up, okay, so these currents basically are established by this this current mirror here. Now this is a kind of strange current mirror because you see here a capacitor here, right? And this is the drain current basically charging the capacitor, and across the capacitor there is a switch here. So what's happening is this capacitor gets charged by the up pulse, right? So when up pulse is there, this capacitor is being charged, and when the down pulse comes in, this capacitor is basically shorted to ground. So what's happening is there is a voltage buildup which basically decides what's the current. So what's the current which is given to the loop filter. So what this is doing is the width of the pulse is going to decide the gain of the charge pulse. And what it does is it's going to give you a very fast settling. So that's the key here. So same thing is being repeated on the NMOS side for the down pulse, but it is slightly more complicated because you are going from the PMOS current mirror to the NMOS current mirror, and then you are implementing the same stuff. Okay, so this is something which is unique here, and I wanted to show you this. Okay, so this is there. So these two things I'll show. Now, as far as filter design is concerned, so there's an algorithm which I have already written, right? So here the frequency is 10 megahertz, loop bandwidth is 1 megahertz, phase margin is 50, gain is around 10,000, right? And gamma is 1, and T31 is basically 0.6, and that results in, let me just show you. Hang on. Okay, so let's see what that results in. Okay. Okay, so that results in this settling characteristics, right? Now, this gives the component values. Cap 1 is 45, cap 3 is 3.3. I'm putting 3.3 here. This I'm putting as 680. This I'm putting as 680 again. This I'm putting as 8 point or 9K, I think 9.3K something. The Xi here is 0.8. So there is going to be a little overshoot and then come down. Okay, so this is all CW, but then what you're going to see here is going to be DT approximation of the CT system. So you have 45, 380, 670 pico, 380 pico, 670 ohms. This is 9.3K. This is 3.3 picofarad. Now, the point to note here is the following. The 3-bit which come from sigma delta, they are added to the course count. Now, this has to be a fraction or not more than 10%. Okay. Reason is your PLL, if you give it a step input, which MASH will give it. Okay, if MASH count goes from 0 to 7, so basically there are 8 states, and those 8 states are added to the count, right? So 8 states in 400 something count is less than 10%. That's what I'm trying to say. If the fine feed becomes a much large percentage of the coarse feed, then the lock is going to throw off, right? So the number of bits of on a MMFD should be such that so in this case 8, so least count is 256, and 8 states in 256, right, is what? It is 24, so it's less than 10%, right? So that's the idea. Otherwise, your MASH sigma delta is going to give you an issue. So having said that, let's see some of the operations. So first, let's see the settling. So because this simulation is going on for quite some time here. Okay, so this is what the settling looks like, right? So it started off from here, and then basically it is going to go through its own ups and downs, right? It's going to go through its own ups and downs, and then will be minor correction. There will be a droop. This will result in some spurs. So of course, you have to take care of all that. There will be a lot of refining beyond that. So let's see what's happening in terms of frequency here. So this seems like this is kind of almost settled. This simulation has been set to run for 80 microseconds, which is very less compared to the entire 2 raised to 16 cycle. So the fraction of 0.25 is not exactly established. Now, another thing is, what is the resolution? Okay, so if you have 10 megahertz, right? So if I go to calculator, so if you have got, let's clear this, go to standard. Okay, so let's say you have 10 megahertz, 1, 2, 3, 4, 5, 6. Okay, 10 megahertz frequency, and I divided by 65536. Okay, so 152 hertz is the resolution, right? But this is not going to be the resolution because there is a divide by 8. So you have to multiply this by 8. Okay, so you are going to have 1.22 kilohertz of resolution. Okay, if you run it for the entire 2 raised to 16, then the resolution you're going to get is 1.22 kilohertz, right? And that's in your 10 megahertz. They are going to be 65536 steps, right? So that kind of fraction you can achieve here, right? So it's good that at that high frequency you have this kind of fraction, but still, let's see what it is giving out in, let's say, 22 microseconds. All right, so let's say it has stabilized at around 10 microseconds, or rather 12 microseconds. So I'm going to see from 12 to 22, which is hardly 10 microseconds. I'm going to see what is the frequency component. So what I'm going to do is I'm going to go to result from main. I am going to plot this voltage. Let's see. It's still doing it. There's so many points. So basically this is the VCR output. It goes from 1.1 volts to 1.8 volts roughly. And then there is net 13 and 14. So let's go to calculator. So the differential out is there. So control C. And here I'll say control V minus 12. So basically this is your peak to peak, negative positive, right? And then I'm going to do a DFT on this, right? So basically on this signal, which I'm going to paste over here, on this signal, I want to go from 12 to 22 micro, right? And say, okay. So this is my DFT here, which I'm going to hit plot. So I hope it plots. Yeah, it does. So it does plot here, and it's showing right now that the frequency is built to 38.418. So basically in this 10 microsecond, so of course it will go through the entire 2 raised to 16 cycles, which is over 1 millisecond. It is going to have an exact 38.5 gigahertz. Right now it is 38.4018. So basically it is like 99 megahertz kind of it has to recover, right? So over the averaging over the sigma delta, you will achieve that number. So it is going in the right direction. Okay, over 10 microsecond I'm seeing it is achieved 30.4. So now if you think about it, if it was an integer n and 10 megahertz is the reference, then your resolution would be 10 into 8, because 8 is the multiplication prior to multimodulus divider, right? So 80 megahertz resolution will be there in a fixed n. Now the way the settling happens, right? So let's get rid of some of them. Let's delete this one. So the way the settling happens is it's first going to achieve the course. So wherever you see these spikes, basically this magenta is the output of the charge pump, and the green is the output of the loop filter, right? So basically magenta is over here. Of course, it is trying to plot it again. So let it plot it again. And then this is the one which is the output of the filter. So yeah, it plotted again. Yeah, so I can delete this one. Okay, so when you start seeing these spikes die out, right? And then the magenta basically follows the green, which means that there is no current in the loop filter, which means all the caps have reached their final value of voltage, right? That's basically where the locking is exact, right? Based on the fraction. But anyways, so what I'm I was trying to show here is that. Now, another thing I want to show is what is unique. So let's go here. So settling will take some more time. Let it run. Okay, so let's go to test benches and test VCO if it is there. Uncategorize test VCO is there. Yes. Okay, I'm going to show you whether the injection locks are working and whether the locking is correct, right? So that's your VCO, right? And this is my control voltage here, right? It's driven from 1.8 volts. These are the bias currents, and inside this is your VCO. Of course, you know, there's no information yet on this simulation. Okay, so that's the VCO which we talked about. So let's go back. Let's go back. Okay, so now check and save. Go to launch ADEL. And here I'm going to do simulation transient and check out the frequency. So let's go to analysis, choose transient, and let's run this for maybe a microsecond. Okay, and we can do conservative. Now this is something which helps in conversions, so I'm going to say just the node voltage and skip the DC analysis for now and say okay and say okay. Now I had to set an initial condition to help the conversion or get the VCO started. So this node, basically I want to have a starting node with a 0 volt is the initial condition. In practical circuit, it will always be, you know, starting from 0 volts. So anyways, so this portion is done, convergence conditions, and then output to be saved. Output to be saved, select on schematic. So this is the output, this is the output, this is divided by 8, this is divided by 8. This is all I want to observe. This is at 1.6 volts at the control voltage. So let's go ahead to the analog. Yeah, so here we are. And what else we need to do? If you want, you can do a high performance computing and number of cores you can set. Well, you can do you can divide your circuit into digital and analog, and then basically apply, you know, speed up the simulation on both digital and analog domains, but I'm not going to do that. Okay, so that's done. Now I'm going to hit simulate. Hopefully two can run together, right? Is there another simulation running? Yeah, so it started. So it's, I don't know if it is oscillating. So let's see what happens. So it's not always that you find DFT. What you can do is in this, there is an algorithm which takes the time period and inverses it. And that gives you the frequency, instantaneous frequency. So we are going to use that algorithm to see what the frequency is. Seems like it's very slow and 1 microsecond is too large. Yeah. So what I'll do is I'll terminate this. Okay. That's okay. We can still plot it, right? Results, direct plot from main. Okay. So this is the output. And this other one is 12. This is 11. This is 10, right? So this is that. And this is the divided frequency. This and this. And if I separate them out, right? So don't worry about how much is the swing. This is your rail to rail swing because you have a divider divided by 8. So I want to check whether divide by 8 works. So this is 10, 11. This is 6 and 7. So I'm going to take the calculator, and this is your 11. Control C, and I'm going to say minus Control V 10. Okay, and to this, I'm not going to apply the DFT. Let's close this. I'm going to just do a frequency on it. Okay. Yeah. So this is done, and I'm going to plot this one. Not working. Oh, just 1 second. Maybe some expression is wrong. Let's go back. Let's clear a lot of confusion there. Let's clear the previous calculations. Okay, so let's do this again. Let's choose this one. Calculate. Let's choose this one to the calculator. And to this one, and this is 10. Okay, so let's plot this one. So that's the swing. So I can get rid of the other two, and get rid of this one, and get rid of this one. Delete. So that's the one. Then I can go back to the calculator, take this, look at the frequency of this, and say okay, and say plot. So that's the frequency, right? So I can get rid of even this one. Delete this. Okay, so same thing I'm going to do for this one. So I'm going to take this one to this. This is basically 6 minus 7, right? So I'm going to say minus, sorry, I'll do this again. Take this one to calculator, select this one, Control C, minus, Control V, and this one is net 7, right? And to this, I'm going to apply the same frequency, instantaneous frequency, say okay, and I'm going to hit plot. Okay, and then I can get rid of these. Delete. What? I deleted the wrong one. Do over again. Is it there? That's the one. Okay, that's the one. Plot. So this one I have to get rid of. Delete. And this one I get rid of. Delete. Okay, so what is this? Okay, so if you see, this is 40 gigahertz, right? And this is 5 gigahertz. So let's pick any point. Yeah, let's pick the last point, because this is instantaneous, right? So this is 40.78. Okay, so clear. This is 40.78. Okay, and then if I divide by 8, I expect 5.0975. So what's this? 5.0945 or whatever. So basically this is a division by 8, right? So the injection lock dividers are working. Right, now let's change the control voltage and go to the other end. So the other end would be this one at around 0.3 volts, 0.3 volts. Check and save and run the simulation again. Again, this is a long simulation, so I will not run it for very long. I just run it for let's say 150, and then again look at whether divide by 8 is working. Right. So this is a wide frequency lock from 37 to 40 gigahertz injection lock dividers. Okay, so this is one key unique thing about this. The other one which I'm going to show you is the charge pump. So let this do 150. Okay, it's done 150. So I'm going to go to this one and hit stop, right? Okay, so once I have hit stop, I can go here and upload, reload the window. Okay, of course, you know, these gyrations you are seeing. Okay, let's put here, because this is too little a voltage. So let's see what is this frequency. This is 36.17. So basically we don't go down to this voltage. Let's change this to something like 0.6. Okay, 0.6 is good enough. That gyrations you are seeing because of, you know, we have gone far below in frequency. Check and save, simulate. So basically injection lock loop has a range. So you will typically start seeing this lock falling off, and you will see these gyrations. So 150 nanoseconds is what I'm looking at. Any next time, any point. Yeah, so I'm going to stop the simulation here, or I can just upload, reload the window. Of course, when you do this and your simulation is still running, it's going to take time. Maybe I can hit stop here. You cannot, because it's frozen. Let it display and then it'll be off. I'll be able to. Yeah, it's trying to plot. The problem is there is another simulation running, so I have allocated some memory to the machine. So come on, guy. I don't want to stop this simulation. Yeah. What? Okay, let me have to plot it again. Result, direct plot from main. We have to do the maths again. Yeah. Control C. I'm sorry about that. I just wanted to show you injection locks are working across band. That's all I wanted to show. Okay. So still you see gyrations or what? Yeah, you see some gyrations. Delete this one. Delete this one. Okay, so this is around 36.4. Of course, you know, you go up 37. But let me see if there's a division by, let's check this one. And this is what, 6 and 7, right? So let's catch this one. Go in here. And I choose this. Yeah. Go in there. -7. C. E. 7. And then you just choose this and look at the instantaneous frequency. Say okay, and then just plot it. And I'll just get rid of this one. Come on, guy. Simulations is still running. That's the reason. Should have switched off the simulations. Oh, Where's ADL4? Where's the root of this? No, simulation stopped. Right click, delete this guy. Okay, now this is 36.1 roughly, and this is 4.96. Okay, 36.1. So let's go to calculator. So we are looking at cancel 36.1 divided by 8. That is 4.51 something. Okay, so it's slightly fallen off. So anyways, what I'm trying to show is at 37 it should be exactly 8. Okay, and because of those gyrations you are seeing, that's why you're not looking at the exact division. Anyways, so this injection lock is doing that. Now another thing which I wanted to show you was test charge pump. Test charge pump. Go to test benches, charge pump. Okay, so that's the charge pump setup. And what I'm going to do here is Q. This is driven by 10 megahertz, right? So this is driven by 10 megahertz. There's no delay here. There's no delay here. Okay, so this is ref and this is diff. This is BFD. This BFD is driving the charge pump, and right now there's no phase difference. So let's see what's the output of the charge pump, and I will start with the initial voltage of 0.9 and see what charge pump does. So I'll go here, launch ADL, go to analysis, choose transient, and I'll simulate for maybe 1 microseconds. And options. Okay, and then the conversion aid. Initial condition on this one, I want to put 0 volts. That's done. Now I want to put 0.9 volts. Start from 0.9, so I can see both sides. So right now it's 0.9 volts, correct? And then I'll go back here and output to be saved. Select on design. I want to save this one. I want to save up. I want to save down. I want to save this, and I want to save this. So what I expect is up and down, up and div, they are together. So let's hit simulate. Okay, so I'll go to results, plot from main. So that's your up pulse, and that's your div pulse. So one over the other, right? And then the output is going to be just spikes. Not this one, sorry. The output will be up and down. Okay, so let's separate all of them out. Okay, so this is slightly biased towards up right now, right? And when nothing is issued, this is slightly biased up. This is something similar to trickle charging. Basically, I'm expecting some leakages, and this trickle charging will take care of that. Now, let's put here, so this is starting at 0.9, right? So let's put here ref as delayed. So div comes first. So that means that div is faster than ref. Then the down pulses will be issued, and this voltage is supposed to go down. So if I go here Q and put in here a delay of 5 nanoseconds. Okay, and this one Q. So this will be 55 nanoseconds, generating a differential, right? Okay, so ref comes 5 nanoseconds behind. I can save, and I will say simulate. Okay, it's done. Not yet. So basically the ref is delayed now, and div comes first, so down pulses will be issued. So if I go here, load. Okay, and these down pulses are going to do this. You can see the voltage is climbing down because they are down pulses. The yellow one is the down pulses, and this is 5 nanosecond wide. So you see that this is going down, right? Now, if I increase the width of the down pulse, right? So let's see if I go from Q, I go from 5 to 15. Okay, and this Q from 55 to 65, right? So now the down pulse has become wider. Now simulate this again. And watch what happens. So I can get rid of this to be clear. Or maybe let it be there. Okay, so I'm going to upload the windows. Now you see the gain basically of the charge pump has changed for a wider pulse. So what that means? That means that if the pulse is up or down, they are wider, then the KVCO, the K phi is going to be larger, and the K phi is going to scale down as the pulse become narrower and narrower. Okay, so now let's do the same thing with the other side. So go Q, and let's remove this delay of 15, and Q, let's remove this delay, make this 50. Okay, so this is a differential nature, and let's say Q, let's issue this a 5 nanosecond delay, apply, and this is going to be 55. Okay, so now the diff is coming after the ref. So diff is behind means that it will issue up pulses, right? So you check and save and simulate this. Okay, so now this charge pump output is going to go up with the 5 nanosecond pulses. So I'm going to say reload Windows. So now you see the up pulses are issued. So these are up pulses. These are down. Basically, this is overlap to get rid of what you call the dead zone, right? Okay. So now again, see the modulation. So let's make this 15, and let's make this 65. Okay, so now the div comes 15 nanosecond behind the ref. So up pulses are going to be wider, right? And that means that the K phi is going to go up. So if I was to upload this, so now you see same thing as what happened with the down. Same happens with the up, a much bigger step. Okay, so basically you have to go up to 40, which is half of the duty, the half of the period, which is the width of the pulse. So up to 50 nanosecond is the total width. So the K phi is going to increase with the width. So this has been applied here. So I hope you understand what that is. Okay, so where are we? So we have seen the PFD, and we have seen the charge pump with the PFD, and we have seen the entire loop. So let's see the loop once again, and then I'll finish off. Okay, so the output of the VCO goes into the multimodulus divider, goes out, goes into PFD, and PFD output drives the charge pump drives the loop filter, and I've shown you how to calculate the loop filter. And the output of the loop filter is the control voltage of VCO. Now, as far the coarse feed is concerned, this adder basically adds the coarse feed to the fine feed. Fine feed is coming from the sigma delta modulator. It's adding that, and that added output is fed to the MMFT, and I have shown you already the calculation how these are calculated. So basically that's a 5G PLL operating from 1.8 volts, covering a frequency of 37 to 40 gigahertz, has 3-bit injection lock divider, which divides by 8, has 8-bit multimodulus frequency divider for fractional N for noise shaping. There is a mesh 111, and there is a PFD, which is a fully differential using PPCL gates, and then there is a charge pump, which is basically scalable charge pump, and that's the 5G PLL. So I'm going to stop here. Thanks a lot for listening. Thank you.